Alright, Chapter 5, States of Matter. So this goes through the different phases of matter, liquid, gas, and solid. Section 1 is an overview, and then Section 2 is all about the gases. So Section 1, you talk about the three major phases. You have solids that are closely packed. The arrangement is a regular repeating pattern. There is no freedom of movement. Volume is definite, and shape is definite. And gases, you have a little close together, as not as close as solids, but they're close together. Their arrangement is random. They're free to move. They have limited movement in all directions. Depends on the shape. Depends on what they're contained in. There's a definite volume, but there's no definite shape because it takes the shape of whatever container you have. Gases are separated far apart. Their arrangement is random. There's no arrangement. They are free to move in all directions. And then the volume is indefinite in the indefinite shape as well. Alright, so here's some other descriptions. Solids you can see, has a definite shape in the beaker. It's not taking the shape of the beaker. It's taking the shape of whatever the solid is. They are strongly bonded, mostly ionic. It depends if it's ice or not. They do expand when heated, usually to a liquid, sometimes the gases, like carbon dioxide. Liquids have no definite shape. It takes the shape of this container, in this case a beaker. They are difficult to compress. They are weakly bonded, meaning they're not holding on to each other as strong as a solid. And they move faster when heated as well. Gases, there's no fixed shape. They diffuse quickly depending on their molecular mass. They're easily compressed. There's virtually no bonding between them. There's just the van der Waals forces. And they bounce around walls and container in random motions. Alright, these are some solids that we basically will cover in this chapter. You have your simple atomic structure that we know and love, a simple molecular structure. You have a giant ionic structure, crystal, like sodium chloride. You have a giant metallic, so metallic bonds here. And then a giant molecular, like diamond, silicon dioxide, graphite. These are more of the non-polar structures. So you can see here you have your three types of bonding: ionic, covalent, and metallic. Covalent can be broken down into network solids. These are your diamond, quartz, silicon dioxides. And then you have molecular covalent, which are small molecules like water, CO2, nitrogen, and then big molecules mostly for biochem, polymers, proteins, DNA. Pretty simple. Alright, 5.2. This deals with gases. So, in a gas, you have constant motion, and basically if it's in a container, it's just a random motion bouncing off the walls, no particular pattern. So, to come up with the kinetic molecular theory, they designed these laws or these theories of gases. So the first to be in the kinetic theory is that gases move randomly and rapidly, which makes sense because these are gases. There's no motion that's been detected, and they are rapidly moving. The distance between gas molecules, that means the van der Waals forces, is basically very negligible. The diameter of the molecule and the volume of the molecule is very small, so it's basically taken into account as very negligible. There's no forces between molecules. That means there's no attraction or repulsion, which makes most sense for most gases, being most gases are nonpolar. And then when you collide, there is no loss of energy. meaning that all the particles is elastic. So the transfer of energy is non-existent. And the temperature of the gas is related to the average kinetic energy, which makes a lot of sense. The more temperature, the more kinetic energy a molecule has. Alright, so an ideal gas. Basically, an ideal gas follows the kinetic molecular theory. So that the sorry, I got interrupted. And then some do not follow the ideal gas law, which are called real gases. Noble gases generally follow the description of ideal gas, particularly helium and neon, because of their smaller size. As the size gets bigger, that means they're going to follow more of a real gas. They don't fit the full description of a kinetic molecular theory because of their size. So as you increase the protons and electrons, you have more van der Waals forces, so you have more interaction. In the smaller molecules, you don't have that interaction, and they follow more of an ideal gas. Alright, two major things that follow that volume depends on an ideal gas is pressure and temperature. Pressure is basically how much force per area, how many newtons per meter squared, which is a Pascal, which is right here. And then temperature, there's three major temperature degrees: Fahrenheit, Celsius, and Kelvin. But we are going to be working with Kelvin. So absolute zero is 0 degrees Kelvin. Sorry, there's no degrees in Kelvin. 0 Kelvin. 0 degrees Celsius, or water freezes at 273 Kelvin, and water boils at 373 Kelvin. So you can see that the three scales, but we are going to work with Kelvin the whole time. Alright, so you can see in this image, you have gas molecules in a cylinder. If you increase the pressure, the volume decreases. So the inverse of pressure and volume is a linear correlation. So an ideal gas will have a volume that varies exactly to the inverse proportion of its pressure. More pressure, less volume. More volume, less pressure. Alright, that and also is related to temperature. If you increase the temperature, you are going to have more kinetic energy, which causes the pressure to change, which causes the volume to increase. So you can see there's a direct correlation between temperature and pressure, or temperature and volume. As you increase temperature, the volume is going to rise because of kinetic energy. Alright, limitations of the ideal gas. They are called ideal for a reason. Not all gases behave ideally. Real gases do not obey the kinetic theory in two ways. The attraction, we talked about that with the larger gas molecules. There's more van der Waals forces, so there's going to be more temporary dipole-dipole moments, and interaction is not negligible. And volume itself, again, back to size, cannot be ignored, so it's not negligible at all. So you can see here with interaction, if you have no interaction, they basically follow in a straight path, which is perfect for an ideal. But in real situations, gases do not behave because they're interacting with each other, and they behave in a curved pattern as so. Now, if you have low pressure, look at the size of the volume of the gas compared to the overall volume. It's very small. It's negligible. But if you were to have high pressure, okay, the volume is decreasing, and now the percent of the gas compared to the overall is very is larger, so it's not negligible. So it's a significant amount of volume of the gas. So low pressure, ideal, and then low mass is ideal. High pressure is low temperature. So molecules are close together at high pressure, so it doesn't act like an ideal gas. Volume of molecules is not negligible because van der Waals forces are present. So the larger the molecule, less likely they'll act like an ideal gas. Attractive forces pull molecules toward each other and away from the walls, and that's again back to its volume of the molecule. Pressure of the real gas is lower than expected for an ideal gas. That means the van der Waals forces causes the attractions of the molecules. And then volume of the real gas is smaller than expected for ideal. That is back also with the van der Waals forces cause the attraction of the larger molecules. Alright, so homework question number 1. What is meant by the term ideal gas? And then under what conditions do real gases differ from ideal gases? Give reasons for your answer. This is a very common question in an AICE exam. Alright, calculation. Calculation of ideal gas. Pretty simple. We use the pervert equation, which is PV equals nRT. P is pressure, V is volume, N is the number of moles, R is your gas constant, and T is temperature. What units you say? Pressure is in Pascal, volume is in meters cubed, the gas constant is 8.314 joules per Kelvin mole, and temperature is in Kelvin. Alright, so here is an example. We're actually going to try something new. See if this works. Try active board. Okay. Alright, so calculate the volume occupied by 0.5 moles of carbon dioxide at a pressure of 150 kPa and a temperature of 19 degrees Celsius. So we have to use PV equals nRT. We have P at 150 kPa. We have volume question mark meters cubed. N equals 0.50 moles. R is our gas constant, 8.314. And temperature to be 19 degrees C. So we have to convert that temperature by adding 273 to it, which is 292 Kelvin. And we need to convert kPa to pascals. 150 kPa, 1 kPa equals 1,000 PA, which is 150,000 pascals. Okay. Probably going to run out of room. That's right. So, plug and chug. P is 150. Looking for V. N is half a mole. R 8.314. T 292. So volume comes out to be 0.008 3 sig figs 09 meters cubed, which is 8.09 decimeter cubed. Okay. Let's go on. Let's see what's next. All right. That's the same question. All right. Example 2. A flask of volume of 5 decimeter cubed, 4 grams of oxygen, and calculate the pressure exerted by the gas. The molar mass of oxygen is 32 grams at a temperature of 127. So again, PV equals nRT. We have volume to be 5 decimeters cubed, which is 0.005 meters cubed. We need to find N, 4 grams, divided by 32.0 grams is a mole, which equals 125 moles. And temperature, 127 plus 273, 400 Kelvin. And R is always 8.314. Alright, plug and chug. P we don't know. V is 0.005 equals 125 moles. 400 and 8.314. Okay. Plug and chug. Divide by our volume. P comes out to be 8.3. That's weird. How many sig figs? 3 sig figs. So it'd be 100 PA, or 83.1 kPa. Okay. Alright, so here is your next homework question. Calculate the volume occupied by 272 grams of methane at a pressure of 250 kPa and a temperature of 54 C. So you need to make sure your units are pascals and moles in Kelvin. Then question B, the pressure exerted by 0.25 moles of carbon monoxide in a 10 decimeter cube flask is 120 kPa. Calculate the temperature in the flask in Kelvin. Alright, other ways to find, or using ideal gas law, is to find the molar mass. We talked about before, using a mass spec is the most accurate, but you can use ideal gas law given the conditions to be as accurate making sure the conditions are right to find molar mass. So a couple ways you can do it. You can plug in the equation N equals the mass over the molar mass and substitute the general equation, or you can find moles and then use mass to find molar mass in a two-step problem. So here is your example. You have a flask of 2 liters, and it contains 5.28 grams of a gas. The pressure in the flask was 200 kPa, and the temperature is 200 Celsius. Sorry, 20 Celsius. Calculate the relative molecular mass of the gas. So that means we need to find N. So using our conversion, we have 2 liters, which equals 0.002 meters cubed. 1, 2, 3. We have pressure, kPa, which equals 200,000 PA. Temperature, 20 C, which equals 293 Kelvin. Okay. So we can plug in our values. Our constant is always the same. To find the moles, so we have 0.002 times 200,000 divided by the right side, and our moles is 0.164. Okay, so to find molar mass, you take mass over moles, 5.28 grams from here, divided by our moles. Oops. And you get 32.2 grams per mole. Okay? It's a little different than the text, but I think this way is a little easier because you don't have to work with a different equation. You don't have to work with the molar mass over molar mass. This one stays with PV equals nRT to find moles, and then you should use that to plug into molar mass equation. All right. Whoops. All right. So this is your last homework question for 5.2, is to find the molar mass of liquid X. You have 0.08 grams of it, vaporized at 100 degrees C. Volume of the vapor is 23 centimeters cubed, so it's centimeters cubed, and the pressure is 1.